Hello, I'm Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be talking about power cycles. This lesson is tied to the course Chemical Engineering 5220, Intermediate Thermodynamics. If you are needing a more basic level, you might check my playlist for thermodynamics. Our goals in this lesson is that by the end of the lesson, you should be able to use the general terminology associated with power and refrigeration cycles and be reminded of the equipment that is used in the most common power and refrigeration cycles. First, let's consider what a generic cycle looks like. If we consider something where we have a high temperature and a low temperature thermal reservoir, then a heat engine takes heat out of the hot reservoir and adds it to this cycle and uses it to produce work. Unfortunately, there are always going to be some heat losses to the low temperature reservoir. A refrigerator somewhat does the opposite of this. It takes heat out of something cold and pushes it into something warm. But the only way to make this happen is by adding work input. When we talk about the measurements of performance of these devices, we're going to use different terms depending on whether or not it is a heat engine or a refrigerator. For both of these, the ratio is going to be what it is that we are getting out of the cycle compared to what it costs to operate the cycle. So for a heat engine, this is going to be the work or power that we're getting out of it compared to the heat that we're bringing in from the high temperature thermal reservoir. Frequently we think of this as our fuel. For a refrigerator that's being used to cool something already at the lower temperature, we use coefficient of performance. And we're going to take the heat being taken out of that cooler substance, Q2, and divide it by the work required to make this cycle operate. If we use the refrigerator as a heat pump, then we're going to be looking at Q1 compared to the W. But in each case, it's the goal divided by the cost. And we always take absolute values so that we get positive answers. Now for thermal efficiency, this answer will be between 0 and 1. For coefficient of performance, we expect the answer to be greater than 1. Now there are many common heat engines. For the ones that we usually look at, the Carnot is our basis for comparison. It's not a real cycle, but it is going to be what we use as our ideal. The cycle I've shown here is a Rankine cycle, a basic Rankine cycle. Basically, you start with something at a low pressure and low temperature. State 1 is shown in the picture here. We pump it to a higher pressure. Then we add heat to it so that we have high pressure steam. And then we extract that energy out of it in a turbine, producing power. And now we need to return it to the original state, so it's now at a lower pressure already. We simply need to cool it in a condenser back to that original low pressure, low temperature state. Now these may be modified with reheat or regeneration. We also have other types of cycles. These next four are generally termed ideal gas cycles. They operate with air and fuel. The Brayton cycle, the Stirling cycle, the Otto cycle, and the diesel cycle, probably you studied in other courses. I will provide in the comments section for the video some links to other videos that you might want to go to see more details about how each of these can be solved. Refrigeration is normally done by vapor compression refrigeration. It is essentially a reversed Rankine cycle. The way it's shown here is truly a reversed Rankine cycle. You bring in a high pressure liquid and expand it in a turbine which is going to produce a little bit of work, and then we're going to heat it, okay, then compress it back to the high pressure, and then cool it. And this is essentially a refrigerator. In reality, the expense of a turbine is not going to justify the very little bit of work output that you get from this. So normally we actually use a expansion valve, a Joule-Thomson style valve at this point. So you always have to have the compressor. You're going to have the two different heat exchangers, and then you need some way to go from high to low pressure. The cheapest way to do that is through a valve. Ammonia absorption is often very commonly used, but it is beyond what we are ready for at this stage. We will come back to ammonia absorption a little bit later in this course. And then finally we have the reversed Brayton cycle. The reversed Brayton cycle, you would most likely think of this in terms of what you could use, say, in an airplane where you've already got a lot of gas flowing through a system, and you can use that to do some cooling. So these are our common refrigeration cycles. Again, I can link you to some other videos that will go into these in more detail. So this concludes our video on power and refrigeration cycles. Thank you.